Hey Learning Birds, this is Mr. Ozarka with another lesson brought to you by LearningBird.com. If you have any questions about the following video, you can email me at mrozarka@gmail.com. Alright, here we go. Alright, so this is going to be a video about the law of conservation of energy. Before we start talking about this law, though, we're going to talk about what energy is. So a quick review, energy is anything that causes matter to change. Okay, and it comes in two forms. It can either be kinetic energy, which is based on movement. So anytime something has motion, then it has kinetic energy. And then also the second form is called potential energy. Now this is energy based on the position of that object. So whether it's in the air or whether it's stretched out, whether a spring is compressed, those are all examples of potential energy. Now the equations for potential and kinetic energy, I wrote them right over here. It says kinetic energy is equal to mv squared divided by 2, or 1/2 mv squared. So again, the mass of some object, so whatever the object is, any object has mass, you would multiply it by its velocity squared and then dividing that by 2. Now this potential energy equation right here, this is actually gravitational potential energy, but it's the one that's most commonly used in introductory physics classes. But it's basically you take the mass of the object times the gravitational constant times its height. So however high it is in the air, the higher it is, the more potential energy it has. Now we're going to talk about what the law of conservation of energy is. Basically it states that energy cannot be created nor destroyed. So energy doesn't just poof vanish or poof appear out of thin air, but it can change forms. So it can't just appear or disappear, but it just changes forms. A good example of that is this cartoon picture I have right here. So there's a cannon right here, and it says chemical energy. Now the chemical energy here is whatever that gunpowder is used by this cannon to fire this missile right here. So the chemical energy is basically this energy that's stored in the chemical bonds. This would be ignited and cause an explosion, so there'd be an increase in pressure. So there's this huge motion, this huge kinetic energy that's produced. And it says right here, this chemical energy is transferred to kinetic energy and potential energy. Now the reason why it's both is because technically this missile right here is moving, but it's also high above the ground. So we talked about that potential energy based on its height. So since now it has its height, now it has potential and kinetic energy. Eventually now it says it transfers this to less kinetic energy and more potential energy. Now the reason why this happens, if you notice the kinetic energy for this missile right here is going up in the air. Eventually when it reaches the top, it stops going up and it just kind of goes horizontal for a split second before it starts going down again. So at the very top it says less kinetic energy. So it's just for that split second at the very top, it's a little bit less. It's still going to the right, but it's not going up anymore. There's more potential energy because it's at its max height. So it's the highest it is right there. So it has the maximum amount of potential energy. So from there, it eventually starts going down. So now it has more kinetic energy, less potential energy until it eventually hits the ground here, and then it transfers or converts to heat, which is the kinetic energy of molecules. So when it interacts with the ground, it's going to cause like a bunch of friction and heat that's produced because the molecules are all kind of bumping into each other. It's also going to produce a lot of sound here, as well as other motion from it moving this earth right here. It's moving the ground. That's a good example of law of conservation of energy. None of the energy actually disappeared, it just converted to different forms. Okay, next we're going to talk about something that's really closely related to this. It's called energy efficiency. Now some devices are designed for specific energy needs. For example, a light bulb. If you have a light bulb, what you want to use a light bulb for is producing light. You don't care about anything else it's producing except for light. Now the problem with old school light bulbs, so I have this right here, these old school light bulbs, they're called incandescent light bulbs, is they produced a lot of heat. Well, most people do not want heat from their light bulbs because it's just a waste of energy. As you can see right here, it says any other energy converted is considered wasted. So this heat that's being produced, you don't necessarily want that. Now, why do we not want to waste energy? Well, energy costs money. The electricity that you pay for costs money. So if you're using less electricity, you're saving more money. On top of that, you're also helping the environment out. So that's why these new light bulbs right here, these newer kind of more energy efficient light bulbs are better because they produce heat, but they produce a lot less heat and focus more on producing a lot of light, which is what we want. So these are way more energy efficient than these incandescents. So the new school, the newer kinds of light bulbs are a little bit better than the old ones because they save you money and they save energy. Another good example of that is cars. So I have this picture of this outline of a car kind of broken down, and it says 100% of energy in a gallon of gas goes into the engine. So you have 100% of that energy. That's what you start with. Now Now, you don't actually get 100% of that energy out. The whole point of a car, the main point of the car, I should say, is to move you from point A to point B. The problem is other forms of that energy, that 100% of the chemical energy that goes into the car, is not used to get you from point A to point B. As it says right here, 17% is lost from just idling. So you're not even moving, the engine moving, but not the car itself is not moving. The engine moving, just idling there, 17% of that 100% energy is just completely lost. 2% is lost in accessories operations. So that's, charging the battery, turning your air conditioning on, turning the coolant system on for the engine, that sort of thing. It says right here, 62% is lost to engine friction, engine pumping losses, and to waste heat. If you notice, cars produce a lot of heat. You don't even necessarily want that heat sometimes. Some of the heat just comes right off of the engine. If you ever touch the hood of a car after it's been driven for a long time, it's very hot. You don't even want that heat, so it's completely wasted. You want it to more go from moving to point A to point B, but instead a lot of that is used. As you can see, 62% is lost from that. 5.6% is lost to drivetrain in the drivetrain due to friction and slippage. And then right here it says 12.6 is actually used to move the vehicle down the road from point A to point B. And that's what we really want, is that 12.6%, but we wish that it was a higher percentage. We just want to move. But out of that 100%, we're only doing 12.6% of it. That's about 8 times less of the energy that you would have gotten from that 100%. Now, you may think 8 times, that's not that much. Well, maybe you do think it's a lot. But if you think about it this way, if you fill your gas tank up once a week, that's 52 times a year. Could you imagine doing that 8 times less? That's like filling your gas tank up less than 7 times a year. Could you even imagine doing that? That would save you a ton of money and would be way better for the environment if you only had to fill your gas tank up 7 times a year. Okay. Now there are advancements in automobiles that they're trying to get so these cars are more energy efficient. If you've ever seen Priuses, what they do is they take some of this energy that's lost and they try to convert it. They try to store it into a battery. That's why it's called a hybrid, because it has gas, but it also has like another battery side power kind of a thing that gets charged from this engine friction and from idling and from other things that the energy would have just normally been wasted on. So that's what scientists are trying to do, engineers are trying to do, is design these cars that are more efficient. I have another example right here for solar power. Now 100% of that energy from the sun, let's just say 100% of it that's coming into Earth, hits the solar panel. Not 100% of that energy gets absorbed by the solar panel. So scientists are trying to figure out ways to get it so as much of that energy is absorbed as possible. So you get a lot of loss just from the straight absorption from the sun. Next is this electric current. Now electric current is when electricity is flowing through wires. Now sometimes the wires, most of the times the wires are not 100% pure. There's sometimes impurities in there that cause a little bit of resistance for that wire. So when the electricity is going through it, it would bump into that little bit of resistance and produce a little bit of heat, which means you would actually lose some of that electricity. So even solar power is not 100% efficient. But again, this is what engineers are trying to figure out how to make better and better is the energy efficiency. So that's law of conservation of energy. So if you have any questions about anything in this video, let me know. If you thought this lesson helped you, please be sure to click "This was helpful." For other great lessons, be sure to check out learningbird.com.